Hello everyone. So we are going to start the part 4 of colloidal dispersion. So here we are going to study the optical property of the colloidal particles. So without wasting any time, let's start. So optical properties of colloid. What is that? We all know or we have observed that whenever a strong beam of light is allowed to pass through a colloidal solution, then a portion of the light it is generally scattered by the colloidal particles present in the solution, which led to the divergence of the light. The light is generally get diverted from the source. If we observe the source at a distance, we cannot ever draw a straight line from the point we are reaching the light and from the source of the light if it is passing through a colloidal medium. This is because the scattering of the light by the colloidal particle present in the medium. So this effect it is also known as the Faraday-Tyndall effect. So if this is a source of light, you see if it pass through a true solution, it will remain as a straight line, but whenever it will pass through a colloidal solution, it will have some sort of divergence. So this is known as a Tyndall beam if we observe it over a dark background. So this is known as the Faraday-Tyndall effect. It occurs due to the movement of the colloidal particle within the solution. So the next part it is the electron microscope. So why we need an electron microscope? The thing is that we have already come across the size of the colloidal particle. We know that the size range of the colloidal particle, with the given specific size range, it is impossible for us to observe the colloidal particle under a generally used laboratory scale optical microscope, because the microscope, the name itself, it reveals the size. It can measure the size in the micrometer range. But as the colloidal particles, they are generally in the nanometer range, so it is very impossible for us to study the colloidal particle under a generally light microscope. So what we can do, we can prefer or we can use electron microscope. The electron microscope, they will actually give a picture of the colloidal particles in the form of, or you can say using an electron microscope, you can get the shape of the particle, colloidal particle. Moreover, the surface area of the colloidal particle, that can be also studied. Moreover, the size of the colloidal particle, that can be studied. The porosity of the particle, and lastly, the density of the particle. So the thing is that the microscope, visible light as a source. So 20 nm size of the particles can be separated and visible using a electron microscope. Now there is a thing that you should have this question in your mind, that all these particles are quite smaller in the size and they are always in a close proximity to each other, right? So how a microscope can differentiate among each and individual colloidal particle? The thing is that we have a parameter, this is known as the resolving power. It is expressed as D. So the resolving power of an electron microscope can be defined as the smallest distance by which two objects can be separated and yet remain distinguishable. Means if the two colloidal particles are very close to each other, the resolving power, that is the D, it is that power by using which you can distinguish among these two particle presence in the colloidal ranges. Means the minimum or minimal shortest distance between which two particles can be easily studied using a microscope. This is known as the resolving power of the microscope. I repeat, the minimum distance between the two colloidal particles with which we can study these two colloidal particles as a separate entity, it is known as the resolving power D of the electron microscope. Now let us see the construction of the electron microscope. So how it looks like externally. If we see it internally, electron microscope have a source of light. Here the source of light, it is the electron. The electron, it is used as a source of light. So generally we have a electron gun here, fitted here. This electron gun will produce an electron beam. So this is the vacuum manifold. So this is the electron beam, and this is the electron beam positioning. It will position the beam to form a straight line. This is the beam diameter reduction, and this is the condenser. When the electron beam is condensed, this is the aperture change, which is also present in your general microscope. This is the aperture diaphragm, and this is the focusing lens. From here, the output is sent to the computer, right? And this is the stage of the electron microscope, and from here the visual transmission takes place, and this all takes place under a vacuum chamber. So this is the electron microscope. It is used for studying the colloidal particles, right? Now the thing is that scattering of the light or light scattering. What is that? You see, this is based on the Faraday-Tyndall effect, as I have already told you. It is widely used in the determination of molecular weight of the colloid. Light scattering can be used to determine the molecular weight of the colloids. Moreover, the light scattering can be used to determine the size as well as the shape of the colloids. So the principle is very simple. See, in terms of turbidity, all measurements are done. So turbidity, it is designated with the tau. This is the symbol tau, right? The turbidity, that is the frictional decrease in the intensity due to the scattering as the incident light passes through a 1 centimeter of the solution. I repeat, the turbidity, it is the frictional decrease in the intensity. Intensity of what? Intensity of the source of light. Intensity of the source of light, whenever the light is coming from the source and it is allowed to pass through a colloidal solution of 1 centimeter, definitely there will be some sort of scattering. This is known as the turbidity. This is designated with tau. So the turbidity can be calculated as follow. We have a general formula. As per this formula, we can write or derive Hc by tau is equal to 1 by m plus 2 Bc, where tau, it is the turbidity expressed in per centimeter. C, it is the concentration of the solute at the wavelength. We have already, wavelength it is given in the per centimeter scale. M, it is the weight of the average molecular, or you can say weight of the average molecular colloid, and which is expressed in gram per mole or Dalton. So now the thing is that this reaction can be rewritten here again. So here I have written, instead of the tau, I am keeping it as a capital T. So Hc by T is equal to 1 by m plus 2 Bc. So where H can be written as H is equal to 32 pi cube n square dn by dc whole square divided by 3 lambda to the power 4, and where this T, or you can use the tau here also, this T, it is the turbidity, C, it is the concentration, M, it is the weight, that is the average molecular weight, B and H, this B and H are a constant. The value of the H is this, the value of H is this. So B and H are constant for a particular system, and this N, it is the refractive index of the solution. Now the solution here, it is the colloidal solution, right? And this is the capital N, this is the Avogadro number. Lambda, we all know that it is the wavelength of light, and dN by dc, it is a change in the refractive index with the concentration. dN by dc, it is a change in the refractive index with the concentration. From here you can find the value of the H. H is equal to this. Done. Now there is a question, why the sky is blue, right? We all know that the source of light that is coming from the sun, it is generally, we have the red and yellow beam, right? But the sky, it appears blue. Why? The reason is very simple. You see, the intensity of the scattered light, it is designated with I, as the intensity of the scattered light, it is inversely proportional to the fourth power of the wavelength lambda. This law, it is known as the Rayleigh law. The Rayleigh law means the intensity of the scattered light, it is proportional to the, inversely proportional to the fourth power of the wavelength. Now the thing is that still the answer is not coming, right? Why the sky is blue? Simple. Does the shorter wavelength light is blue? the blue have a shorter wavelength. I hope you all remember the VIBGYOR, VIBGYOR, VIBGYOR. These are arranged as per their wavelength, right? The blue have a shorter wavelength. Thus, the shorter wavelength light is blue, which is scattered more intensely as compared to the longer wavelength yellow and the red. So, thus scattered light is mostly blue, where transmitted light has a yellow or reddish color. I repeat, due to the shorter wavelength of the blue color, the scattered light is always blue from the sky, whereas the transmitted light is either yellow or reddish. So if we arrange the wavelength of the light VIBGYOR, so Y and R, it remains in the lower part with a bigger wavelength, right? The blue, it have a smaller wavelength. I hope it is clear to you. Thank you once again. If you like the video, just press the like icon. You can share this video and you can subscribe to my channel. Thank you once again.